Hello, everyone. I'm Jacob Steinhardt. I'm one of the instructors for the Spring 2020 Data 102, together with Moritz Hart. So Data 102 is a fairly new course at the senior level. It's called Data Inference and Decisions. And our goal in this class is to really get students to think critically about the entire data science pipeline. So the relationship between the actual world, the data you see, the model you're using, and then the predictions and decisions that you're making based on that model and how that ties back into the world. And one of the key points here is that in all of these steps, there's assumptions and there's abstractions, and we actually need to think carefully about what these mean to think about the actual real world consequences of the predictions and decisions from the models we're making. So some maxims that we gave to the students along these lines are things like all models are wrong, but some models are useful. The math is not the territory. But we're going beyond just thinking about the relationship between a model and reality. We also want to think about things like data collection. So here's an example where the problem can arise at the level of data collection. There was this artist who was, for reasons that I don't quite remember, annoyed with Google Maps. And so to protest them, what he did was he just got a bunch of Google phones. He turned on navigation, he put them in a wheelbarrow, and he put the wheelbarrow in front of Google Berlin, which then showed Google as having tons and tons of traffic around it because of these phones, which were used to forecast traffic. So this, in some sense, is kind of a comedic example, but there are many cases in the real world where there can be disconnects between data and reality. And we talk about those throughout the course, including, given this semester, some examples of how this can happen for COVID-19 tracking. So just to give an overview of some of the course topics, we talk about modeling and data collection, as I just discussed, and sources of error there and elsewhere. Also implications of modeling assumptions. So one example we gave, for instance, was election forecasting during the 2016 election, and how many models had independence assumptions baked in that aren't really true, and as a result, we're far too confident that Hillary Clinton would win. Another issue is robustness, so how well models do out of distribution or when their assumptions are violated. And a really big focus is real world consequences of decisions. So thinking of statistical or data science algorithm, not just as a sort of abstract thing on a computer, but a thing that actually affects things in the world, and thinking about how that happens. And as a result of that, we also talk a lot about human context, so issues like fairness and privacy. So I think what I want to do next is just give some examples of some of the pedagogical techniques that we use. So one that I think is very helpful for a course like this is case studies. So we'll often present some technical points, but then try to get students really thinking about it and tied into other parts of the course via a case study. So one example was something called the Framingham risk score. So this was a study in heart disease in Framingham, Massachusetts, with about 5,000 subjects. It monitored those subjects for 10 years, and then looked at which patients developed heart disease during this time frame and used this to build predictors of heart disease risk. So they basically just kind of, you have to worry about censoring, but basically from this data, they build a regression model to predict the risk of heart disease. So we described this study to the students, and then first we asked them, okay, you're building a regression model. We all know for regression models, we need to pick our covariates or our features. So this was more of a warm-up, but this was just to get them thinking about the problem set, and we asked them what features would you use. they came up with a lot of good ideas, and then we discussed the actual features that were used, which they mostly were part of their suggestions. So in this case, it was age, gender, cholesterol, blood pressure, hypertension treatment, diabetes, and smoking. And this is there's actually just websites you can go to that really do let you just enter these features in, and it will give you a risk score. So this sort of helped underscore that this is a real thing that is actually used by doctors to make real decisions. And so once we completed this warm up, then we asked them to kind of think about, okay, if you were designing this, what are the sorts of potential issues you would need to worry about? And are there any things we need to worry about for, say, the study design to get a good score? And I guess so we had them do that as another brainstorming exercise. And again, they came up with a bunch of ideas. There were a couple that in some sense we were fishing for here. So the really big one was distribution shift. So it turns out that the large majority of the people in the study were white, and there are kind of racial factors in heart disease risk. So this model makes reasonably good predictions on white individuals, but is inaccurate for other races, especially Hispanics, actually. So this allowed us to discuss issues of robustness of models to distribution shift, and how just because a model is accurate on its training distribution doesn't mean it's accurate on other distributions, which is a sort of important underlying concept for a lot of our material. And we kind of discussed how we could fix this, and then we also tied this back to a previous unit on fairness, and this allowed us to also kind of see in a richer way how, for instance, socioeconomic factors in society can affect studies designs, which then affect models, which sort of feed back into the prediction. So this was a sort of nice way of tying this in with other topics as well. So as an example of one case study, and you can see how this both lets us kind of deepen the material within a single lecture, but also tie it back to other lectures. Another case study that we talked about was observational studies on sleeping pills. This is actually going to be replaced next year with an almost identical example on hydroxychloroquine, which is a drug that has been considered for treating COVID-19. So for sleeping pills, the basic point is that there's many studies that they're observational studies, but they observe that the patients who take sleeping pills have higher rates of mortality under almost every single cause. And so this might lead you to believe that it's quite dangerous to prescribe sleeping pills. But since these studies are observational, you might be worried about confounders. And so people showed that if you control for various confounders, you still see this effect. But I think you should still be sort of suspicious, because the fact that it affects kind of all causes, including fairly unrelated things like heart disease, suggests that there is probably some common cause like stress that both increases mortality risk and increases the need for sleeping pills. And indeed, there's sort of recent studies that show that if you control for enough things, then these effects go away. And so we use this as a springboard for discussion, both on kind of issues of observational studies, causal inference and confounding, but also to discuss what controls actually are. So I think in general, a big problem in a lot of kind of applied fields that use statistics is that controls are kind of viewed as a panacea. But controls really are not, they have a lot of limitations. Often they're only controlling for linear effects or otherwise sort of involve some modeling assumptions that are probably false. And so we kind of discuss this with the students and discuss kind of warning signs for when you should be especially worried about whether inferences from an observational study are well-founded. And the thing that's kind of cool is even though we gave this lecture before any of the COVID stuff happened and before any of these studies on hydroxychloroquine, basically all of the exact things we talked about, both in terms of the issues with the sleeping pill studies and the red flags you should look for, have shown up in the observational studies on hydroxychloroquine. And at least one of those studies was so bad that it was retracted and was sort of widely criticized, but not before it had ramifications on public health decisions. And so this is something that I think can be a nice tie-in to kind of contemporary real world consequences. So those are some case studies. I want to also next talk about one of our units, just so that you can see how everything ties together. So we had a unit on time series modeling, and this was actually after the COVID-19 outbreak. And since there's lots and lots of time series in COVID, we use this as our application example. But we started with just the math, talking about time series, exponential growth models, logistic growth models. We went through some kind of live Python demos to kind of simulate these and create graphs. And then we went really applied. So we talked about time series models in the context of COVID. We talked about all sorts of issues like time lags, over dispersion, underreporting, and things like this. And after some discussion, we finally were able to explain why hospitalizations are often the most reliable tracker of the effects of COVID, because they have lower Poisson noise than death counts, and they have less underreporting and other issues than case counts. And this is something that I think is actually quite underappreciated right now, even among public health officials, but it's something that you can explain with just a little bit of context to someone who has some statistical background. So this ended up being a nice discussion, and it led to sort of further discussions on statistics behind COVID-19 on our Piazza forum. So this kind of tied things into this real world example. And then we reinforced these ideas with some follow-up assignments. So let me switch my screen share to that. So here we go. So the next Monday, we had our discussion section on generalized linear models, which are kind of needed for doing a lot of the time series modeling. So the TAs kind of went over a lot of these ideas. And then on Wednesday's lab, we had a lab on using generalized linear models for time series modeling. We introduced students to the stats models package, which is a useful package for doing this sort of modeling. And then they kind of walked through a bunch of coding exercises and did things like computing confidence intervals and other things like that sort of reinforced the ideas from lecture. Yeah, that's just an example of one of our units. I think I'll wrap up there. This is like I said before, this is a fairly new course. We're still kind of continuing to innovate on the material, but we're really excited about it because it really does tie together a lot of the stuff that people have learned in previous courses and brings in a lot of sort of human context in real world decision making, and has students think critically about that. That's something that has gotten a lot of positive reviews in the course evaluations. And so we're looking forward to future iterations of the course as well. Thanks.